Hey algebra students, welcome to your first flip lesson. This is really no different than taking notes in class. It's still me giving the notes. You're going to take notes on your notes template. This one should be the algebra sets of numbers notes. The benefit to the flip is that you can pause when you need to, if you need a little more time to write, or you need to take a break, and that you can rewatch them if you need to. Just make sure you're jotting down any questions you might have, and make sure you're bringing them into class tomorrow. So let's get started. So we're going to talk about the natural numbers, and hopefully you learned about this last year, but please don't be afraid to ask any questions. Just make sure you're jotting them down, or you can enter that on Edpuzzle. So the natural numbers, they're the set of the natural numbers, has the symbol of the n with a double bar, or sometimes you'll just see the n written kind of fancy in cursive. And the roster, that's the listing, we put that in set braces. And the natural numbers are your 1, 2, 3, and on. So we do dot, dot, dot to show that they continue in that direction. And with that, then we realize that the natural numbers are simply your counting numbers. So the examples of natural numbers would be 1, 2, 3, etc. 7, 43 is a counting number, 2001 is a counting number, etc. Non-examples would be anything negative, anything that's fractional or a decimal would not be a natural number. Anything that's irrational, which we'll talk about for a little bit, and 0 is not a natural number. So the counting numbers start with 1, and they are the numbers that you can use to count. Then when we expand out from the natural numbers a little bit, we get the whole numbers, and the whole numbers are values with no fraction or decimal parts. Or negatives. So whole numbers have no fractions and decimals and no negatives. So when we look at whole numbers, we are looking at the symbol being a W with the double bar. So just looking at a regular kind of W with the double bar, or sometimes it's just a fancy cursive W, but mostly with the double bar. Then we look at the roster, and that's the set list, and that just is the same as the natural numbers, but this time we start with 0. So we do 0, 1, 2, 3, dot, 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 to show that it continues on forever in that direction. So examples are all your same thing as your counting numbers: 2, 1, 3, 0, 5,042, etc. Things that are non-examples, things that are not whole numbers, things that are negative, things that are fractional, things that are irrational. Those are non-examples. So expanding out from whole numbers are integers. Integers is, an integer would be a number that can be written without a fraction or decimal part. Now that's very similar to whole numbers, but the difference here is that integers can contain negatives. So the symbol for integers is a little different. That integers is a Z. Now it looks a little bit like a capital I, but it's really a Z with a double bar. And where that comes from, that little thought process, so here's my thought bubble here, is from the German word for Zahlen. So anyway, that's why that's the symbol for integers, is a Z. And the roster here continues in both directions. So we'll make a nice wide roster there. We would have 0, 1, 2, 3. We're expanding out from the whole numbers. and dot, 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 because it continues to the right there in the positive direction. But integers also continue in the negative direction. So we want to continue a little bit to the left there, and dot, dot, dot to show that that continues to the left. So integers would be anything that is, a number that you could use to count, 0, 21, but also like negative 12 and negative 42 and 1,000. And it is really whole numbers and their opposites. Non-examples would be things that are fractional, things that have decimals to them, and things that are irrational. So a rational number is any number that can be expressed as a fraction or as a quotient of two values. So any number that can be expressed as a fraction. Now, where the word rational comes from is that you know that a fraction is a ratio between two values. So that's where that word, the ratio in rational numbers, comes from. And that symbol is a Q. Now, where does the Q come from in rational numbers? And again, little thought bubble here. The Q comes from the word for quotient. Quotient is the answer word to division, and a ratio is two things that are being divided, something divided by something else, so numerator over denominator. So it's kind of all related together. There is no roster list for rational numbers, but we have examples. We certainly have examples. Anything that can be written as a fraction. Whole numbers like 3, that's a rational number because I could write it as 3 over 1 or 6 over 2. You can have decimal values are rational numbers because I could write them as their fractional equivalent. Mixed numbers are rational numbers. Negative numbers can be rational numbers. You can have negative fractions. You can have negative decimals. Non-examples would be any decimal that goes on forever without repeating. So repeating decimals are examples. Let's put that over here. We have 0.24 repeating. That is rational because repeating decimals can be written as a fraction. Non-examples of rational numbers, again, would be any decimal that goes on without repeating. Square roots of any prime numbers or values like pi that go on forever without repeating are not rational numbers. So irrational numbers are basically numbers that are not rational. So they are, an irrational number would be a number that cannot be written as a ratio. Of integers, so it cannot be written as a fraction. And irrational numbers, very similar to the rational number symbol, so you really have to watch that. It is the Q for quotient, and then there's a bar on top of it, and that is the complement of in math, or not. What is not? So that's the symbol that's coming for that. There's no roster for irrational numbers. But irrational numbers would be values that go on forever without repeating. So if we just have like 3.26719, no pattern repeating, then we see dot, 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 dot going on. Pi is an irrational number. The square root of prime numbers would be irrational numbers. Non-examples, any of your other values, anything that could be written as a fraction, or any repeating decimals are not irrational because you can write them as a fraction. And then all the numbers that we've talked about so far are members of the real number system. So that's really just any value that represents a quantity along a continuous line. The symbol for the real numbers is an R with a double bar, or sometimes just kind of a fancy cursive R. No roster for real numbers there. It would be too many things there. And it's really all the example we've talked about. Any value that exists in real life is a real number. Non-examples are imaginary numbers, and I know that just sounds probably a little crazy, but imaginary numbers will come up in Algebra 2, and they begin with the square root of -1. But we won't really talk about those. You'll get into those in Algebra 2. So basically, any of the values that we're going to give you are real number values, and we'll be looking at that real number system only. So we did just look at the real number system. Another way that's pretty common for the real number system to be kind of looked at is through a diagram or a Venn diagram. And so this whole drawing is going to represent the real numbers. Or we'll use the symbol there. And in the real numbers, then you have them split. The real numbers are either rational or irrational. And then if a number is rational, if it can be written as a fraction, then we look, okay, does it have any fraction or decimal parts? If it does, then it just stays out here in the rational portion. So if it has fractions or decimals, then it just kind of stays out here in this part. But if it doesn't, then it can move into an inner circle here, the integers. Remember, the integers are whole numbers and their opposites, so no fraction or decimal parts in there, but you do have negative values in there. Then as we're kind of moving inward, if a number is not a negative, then it can move, it has no fraction or decimal parts, and it's not negative, then it can move into the whole number portion. And then if it's not 0, then it can count as a natural number. And so it's kind of a moving inward just depending on the criteria of the numbers. So you can see by this diagram that all the natural numbers are whole numbers, all the whole numbers are integers, all the integers are rational numbers, and all rational numbers are real numbers. Now, also irrational numbers are also real numbers, but irrational numbers are not members of the other circles. Now, we'd like for you to be able to classify numbers into their categories. So we're going to take a look at that, and you probably want your Venn diagram, to be looking back and forth to your Venn diagram. So you're looking at 0. 0 is a real number, so we can check that off. 0 is a real number. Now, once a number is a real number, then you're looking at deciding between rational and irrational. So we're looking at deciding between those two. 0 can be written as a fraction, could be written as like 0/4 or 0/12. So that is rational. Now, once something is rational, then you're looking, okay, does it fit into any of the ones to the left? Well, 0 doesn't have any fraction or decimal pieces. It is a whole number. whole numbers are 0 and their counting numbers. But natural numbers don't include 0, so we stop putting check marks there for 0. Now the number 11 is a real number. I can write 11 as a fraction, 11 over 1 or 22 over 2, etc. So it's rational. Once it's rational, I can look at the rest. 11 does not contain any fractional decimal parts, so it is an integer. It's not negative, so it's also a whole number. And it's not 0, so it's also a natural number. Then we move to 3/8. 3/8 is a real number that exists on the number line. It can be written as a fraction because, well, it is one, so it's rational. But it's a fraction or decimal part, so that's all the further we can go on the categories. 3 and 51/100ths, or 3.51, is a real number. It is also rational because I could write it as 3 and 51/100ths, or I could change that mixed number into a fraction. So it's rational. But because of the fraction or decimal part, the 0.51, that's all the further it goes. It cannot be an integer because integers don't have fraction or decimal parts. 2.17 repeating is a real number. Because it's a repeating decimal, you can write it as a fraction. And so that is rational. But because it has that little piece onto it, that 0.17 repeating, it is not an integer. -6 is a real number. It is rational. I can write it as a fraction, -6 over 1, -12 over 2. It does not have any fraction or decimal parts, so it is an integer. But because it's negative, it can't go into the whole numbers, so that's where we stop with that one. Now the number pi is a real number. It does exist along the number line. It's hard to place, but it does exist there. It is, however, not rational because I can't write it as a fraction of integers. That value goes on forever. Now we approximate it as 3.14, but that's just an approximation. The actual value of pi is irrational, and we can't write it as a fraction. Now remember, please take any questions and either put them into the question box on Edpuzzle or bring them into class tomorrow. I'll be happy to answer them.